In this video, we'll introduce the WKB method, and then we'll talk about the WKB approximation, and then the WKB solution in the classical region. So the Wenzel-Kramers-Bruand, or WKB approximation, is a very useful technique for obtaining approximate wave function solutions of one-dimensional systems where the potential is a function of x. That is, it varies, but it varies slowly compared to the de Broglie wavelength of the particle. So let's consider a particle of energy E moving in a region of constant potential V, which is less than E. So we can imagine that E is up here, V is down here, and because if you recall, this is a free particle with a net momentum, which is E minus V. It has a wavelength, a de Broglie wavelength. That is, it also has a wave number and has an amplitude. So it's basically a free particle moving in the positive or negative x direction. And therefore, we know how to solve that. Now, suppose that instead you have a slowly varying potential instead of having a constant potential. So now the potential varies slowly, but it's very slowly on the scale of the de Broglie wavelength. So what's going to happen? Well, you can see that where the energy is higher compared to the potential, then the de Broglie wavelength will be shorter, and the wave number will be smaller, larger rather. So the wavelength is shorter, and the wave number is higher. And as the potential rises, then the wavelength gets longer, and the wave number is smaller. And so the wave number depends on the position because the difference between the energy and the potential is changing. And also the amplitude will change slightly if this is varying slowly as well. So it might be larger over here where the potential is much lower than the energy, and it gets smaller over here where the potential is a little bit higher and closer to the energy. The WKB approximation treats the wave function in this kind of varying potential as the same oscillatory function, but with a slowly varying modulation in both amplitude and wavelength or wave number. So the wave function for the constant potential is that of a free particle, and we know how to write that down. Its psi is equal to a e to the plus or minus ikx for a free particle, where k is just the square root of 2m times quantity e minus v all over h bar. Now, if we relax the condition for a constant potential, but require that its spatial derivative be small over the scale of many wavelengths, and we have a condition for that, that is the wavelength, which is 2 pi over the wave number, is much less than the potential divided by its derivative. So if its derivative is small, the potential divided by the derivative is large, and that needs to be much larger than the de Broglie wavelength, which is given by this, 2 pi over k. The wave function then must become a variable in both amplitude and wave number, and we can then rewrite the wave function as psi of x is equal to a of x e to the plus or minus I k of x times x, and k, of course, also now varies with x, and you now replace e by v of x in here. This also holds for the case where the energy is less than v of x, surprisingly, even though that is not an oscillatory wave function. It's an exponential rising or lowering wave function, as we'll see later. And in that case, psi of x then becomes a of x times e to the plus or minus kappa of x times x, where kappa is just given by the square root of 2m, and now since potential is bigger than the energy, you have square root of v of x minus e over h bar. Well, let's assume then we have e is greater than v of x. So we know that given the WKB approximation, we have a wave function that is a of x e to the plus or minus I k of x x, and k of x is equivalent to square root of 2m times the quantity e minus v of x all over h bar. And for e is less than v of x, we have the similar thing with kappa. So we have psi of x is equal to a of x e to the plus or minus kappa of x times x, where kappa of x is square root of 2m quantity v of x minus e over h bar. We know that this approximation, the WKB approximation, must break down by definition at the turning points. Because at the turning points, E is approximately equal to V. So then lambda and 1 over kappa go to infinity. Right? Because now the difference between E and V is very small. And so those are called the turning points. In a classical motion, that is a turning point of the motion, where the potential energy and the total energy are equal. That's where the particle cannot go beyond, right? And so in a classical system, the particle would stay between this edge here and this edge here, which is the classical region, and the turning point, between the turning points. Now, let's consider for the classical region that a particle is confined to stay in that classical region, right? And so we have infinite boundaries on the edges, and we have this varying potential in this classical region, where the energy is above the potential energy. The total energy is above the potential energy. We can now rewrite the Schrödinger equation in terms of the classical momentum. So, the Schrödinger equation, in this case, because the potential is always less than, potential energy is always less than the total energy, is d squared psi by dx squared is equal to minus p squared over h bar squared psi. And where the momentum is given by 2m, square root of 2m times e minus v of x. And p, of course, is a function of x in this case, right? So it's not a free particle, but it's a particle that can be free with different wavelengths all throughout the region. Now, let's assume that the amplitude, a of x, and the phase, phi of x, of the wave function are real, and they depend on x. So we're going to write our wave function psi of x is equal to a of x e to the I phi of x. We can take the first derivative to apply this to the eigenvalue equation here, as the first derivative gives us a prime, the first derivative of a, plus I times a times phi prime, all times e to the I phi. And we take the second derivative, and now we have a bunch of terms. So first we have this term here, which gives us a double prime, so the second derivative of a with respect to space. Then we have this term here, and we take the derivative of a, so it's 2i, a prime phi prime. And then we have another term, I a prime phi prime, when we take this term and the derivative of e to the I phi. So that gives us two of these. Then we have I a phi double prime when we take the derivative of this term and phi prime. And then finally, we have minus a phi prime squared when we take this term and the derivative of the exponential, all times e to the I phi. Now this is now the second derivative of psi, which is equivalent to this, and we can now equate it to minus p squared over h bar squared psi. And so that equals minus p squared over h bar squared times a e to the I phi. Well, clearly, e to the I phi can be canceled here. And we get then the following equation. A double prime plus 2ia prime phi prime plus ia phi double prime minus a times phi prime squared is equal to minus p squared over h bar squared times a. And this is the equation we need to solve for both phi and a in order to solve this Hamiltonian for an arbitrary potential v of x, which is incorporated into the momentum, right? Because the momentum contains potential. So we start with this term, this equation, and we now can break this up into two equations. One is an equation here written in red, which is an equation for A. So the real equation, which doesn't have any imaginary components, has to stand on its own, and the imaginary equation has to stand on its own. So the real equation is just a double prime minus a times phi prime quantity squared equals minus p squared over h bar squared times a. Well, I can rearrange this and say that a double prime is equal to a times the quantity of phi prime squared minus p squared over h bar squared. And then I take the imaginary equation over here, and I can recast this and set that equal to 0 because there's nothing on the right side. So 0 is equal to 2a prime phi prime plus a phi double prime. And if I multiply by a, both terms by a, then I get 2a a prime phi prime plus a squared phi double prime. And this is an exact derivative of a squared phi prime, all primed. Right? Because if I take this derivative, I'll get 2a times a prime times phi prime. And then if I take the derivative of this side, I get a squared phi double prime. So now I've reduced this to a much more simple form. Well, I can solve this. I can see that this means that if I take the integral of this, it's going to be equal to a constant, which we'll call b squared. So a squared phi prime is equal to b squared. Or a is equal to a constant b divided by the square root of phi prime. We still have yet to solve for phi prime, but at least we now know what a is going to be once we get phi prime. The equation over to the left side, the real equation, can't be solved easily. So this is where the WKB approximation comes in. If we assume that a varies slowly, right, so the amplitude varies slowly, that's the same as saying the potential varies slowly, then we can say that the second derivative of a is much, much less than the derivative of phi squared, or p squared over h bar squared. And so we're going to cancel that. We're going to set it to 0. So if we cancel this, we now get a 0 on this side, and now we have a simpler equation that we can actually solve. So now our equation becomes, under the WKB approximation, phi prime squared is equal to p squared over h bar squared. And if we take the square root here, we see that we have the first derivative of phi with respect to x, which is phi prime, is equal to plus or minus p over h bar. And the plus or minus comes from taking the square root of this. Now remember, p is always positive in this case because the energy is bigger than the potential energy. So the WKB approximation gives you a simple differential equation for phi of x, which solves by integration. So phi of x, you just integrate this equation, you get phi of x is equal to plus or minus 1 over h bar times the integral of p of x dx. And now we've explicitly put back the x dependence of p because it depends on v of x. If we combine this with the solution for the amplitude, which was a of x is equal to b over the square root of phi prime of x, we realize that this is simply just a different constant c which is proportional to b with square root of h bar, divided by the square root of p of x. Because when we take the first derivative of phi, we're going to get 1 over h bar p of x, plus or minus 1 over h bar p of x. So now our solution becomes psi of x is approximately equal to c over the square root of p of x times e to the plus or minus I over h bar integral of p of x dx. Remember, it was e to the I phi, so we have an I left over here. And phi being this integral times 1 over h bar, this is our solution. The modulus squared of psi of x is simply c squared, modulus of c squared, times divided by p of x. So the probability of finding the particle at a point x is inversely proportional to its momentum. So the higher the momentum, the less time the particle will spend in that region. And the lower the momentum, the more time it spends in that region. The general solution now can be written as a linear combination of the plus and minus exponentials. So that is the same as saying a particle going to the right and a particle going to the left in x, positive and negative values. So psi of x then is approximately equal to, under the WKB approximation, of 1 over the square root of p of x times the quantity c plus, the coefficient c plus, e to the I phi of x, plus c minus e to the minus I phi of x, where phi of x is given up here. Similarly, we can rewrite this as a sine and cosine, combination of sines and cosines. It's equivalent. And we get 1 over square root of p of x times c1 sine phi of x plus c2 cosine phi of x. These are two equivalent formulations because e to the I minus I phi and e to the minus plus I phi can be converted into sines and cosines.